make trying to make to see how these invisibles that we discussed before may shed light to mysteries in particle physics. In particular, I will say a few words about the matter-antimatter asymmetry of the universe, or why are we here? And a bit more connecting to experiment, I will talk about recent results of the wobbling effects of muons in the G-2 Fermilab experiment. Oops, sorry. So, oops, I'm sorry, I moved. So let's start with saying very basic, what is particle physics? And so, particle physics is the study of particles and radiation to understand the most fundamental constituents of reality and the laws by which they interact. As we all know, is based in relativistic quantum field theory that really describes particles as excitations of quantum fields, and they carry some quanta that could be mass, spin, and various kinds of charges. So the successful model of particle physics took 50 years to develop. And it has been basically developed by uncovering some fundamental symmetries and interactions and degrees of freedom. And what we know today is that what we call modern particle physics is defined as what we call the standard model, which is a beautiful and elegant mathematical structure that is based in a symmetry group that is SU3 cross SU2 cross U1 that actually describes the strong interactions and the electroweak and electromagnetic interactions. And I will go back to that in a moment. And basically there are 17 different particle fields that I will tell you a bit about more in a second. So moving on, the standard model has matter fields, and here they are, and some force fields, the force carriers. So 12 spin 1/2 fermion matter particles. Here we have the 6 quarks, 3 charged leptons, and 3 neutrinos. And of course, these has at the degrees of freedom because have color and are also doublets under the weak interactions. And there's U2 left. And then there are the force carriers that are these spin 1 bosons that mediate, as I said, the strong interaction, the gluons, the weak interaction, W and Z, and the photon. And in the center here, now more real than before, is the spin 1 zero Higgs boson. So all these particles have been produced in the laboratory. And as we see here in kind of a snapshot, they have very different masses, quite different, like by orders of magnitude. So the question that we first will pose today is what causes these fundamental particles to have mass? And the answer is the invisible Higgs energy field. So that's our first actor of the day. So this is a field of energy that permeates all of space. And let me just first introduce you that, so the one simple invisible field that we are more familiar with is the Earth magnetic field. So this is sourced by the Earth itself and by rotating over its axis. And one can see that it is there because if we have a compass, it defines in the direction of the needle. So we know it's there. The other field I want to introduce to you today is the Higgs field, and I hope it's obvious to you that is here where I'm marking it. So the Higgs field is also invisible, it's so sourced by itself, and it permeates the whole universe. And it doesn't have a specific direction, but we know it is there because, as I will show you, it's responsible for making all the particles which have fundamental particles which have mass to be massive, and therefore it makes the universe behave the way we see it today. So what we think is that the Higgs field turns on itself everywhere in the universe at the first instance after the Big Bang, so 1/10 of a billionth of a second after the Big Bang. And in that process gives mass to the particles that I just, so all these particles of the standard model that are massive, with the exception of the neutrinos, that although they do get some mass from the Higgs, they could have another source of mass as well. So the question is, or the question we'd like to ask today is, what turns the Higgs field on? And the answer is itself, and we will go into that. and how it happens, and that's a bit more tricky in the sense that this is actually through a process that we call spontaneous symmetry breaking. So, so the Higgs field, which is basically defined by this Higgs potential here. So this is the Goldstone Mexican hat that shows this Higgs potential in a simple picture. So the Higgs field potential describes the energetics of turning on the Higgs field to a certain complex value. And the fact is that because of the self-interactions of the Higgs and actually the mass and the sign of this mass term here, the Higgs field self-interactions can energetically favor a non-zero vacuum expectation value of the Higgs. So it's energetically better to be in this valley rather to be in this upper part of the Mexican hat. So as we see here, because of the symmetry that we see here, they are clearly degenerate vacua. And so normally one thinks if they are degenerate vacua, that means that there is a spontaneous symmetry breaking when we pick one of these vacua. But that's not necessarily the case. And I invite you to think about the double well quantum mechanic problem, where the degeneracy of this that is associated with the C2 symmetry implies that there are two possible solutions for the ground state, but the real ground state is actually a combination of the two solutions in a way that the vacuum state preserves the symmetry of the system. So there is now not a spontaneous symmetry breaking in that case. In this case, however, is different because once we decide to take a value of this vacua, it takes infinite amount of energy to move from one solution to another. And this is because in quantum field theory, there are infinite degrees of freedom. And so once one of the degenerate ground states is chosen, it is very hard to transition from this one to the other. So that is the actual process of spontaneous symmetry breaking, which means that there is a symmetry of the system that is not that is not respected by the ground state. And this is very interesting. What I want you to observe here is what I say here. This is because there are infinite degrees of freedom in quantum field theory. That's the reason for spontaneous symmetry breaking. So moving on, as I said, a spontaneous symmetry breaking implies that there is a symmetry of the system that is not respected by the ground state. And in reality, this is a concept that is from condensed matter. So it is a condensed matter idea that is applied to particle physics. But now the quantum vacuum, in this case, is the medium. And this was first observed by Nambu in his novel lecture. He actually said that the spontaneous symmetry breaking in particle physics is a case of cross-fertilization. So let me go a little bit on this because it's important. So the key point here is now that the quantum vacuum behaves as many-body system in this sense. And there are many examples that I put here that are from condensed matter. And so the point is that what happens that there is, even though it's difficult to transition from one vacuum state to another one, there are actually small excitations here that correspond to locally deforming along the valley. And these small excitations are associated to what we call the massless Goldstone mode. So what it means is that here in a U1 phase symmetry, we have a one generator. And when the symmetry is broken, this generator is broken. And in principle, there should be a massless Goldstone mode associated to this symmetry breaking. So that was the problem that Nambu and Anderson and many others were asking themselves almost 50 years ago. If this occurs this way, where are the massless Goldstones? Okay, so, okay. So the real question one can pose really is who really invented the Higgs mechanism? And in fact, as I said, it's a cross-fertilization. And what happens is that Anderson here, okay, was the first to explain that inside the superconductor, spontaneous symmetry breaking occurs because of Cooper pairs. So the electron pairs condense because of the interactions between electrons and phonons, okay? And they break quantum electrodynamics inside the material. Okay, that sounds good. So then where is the Goldstone boson? What happens is that this massless Goldstone boson, that is 1 degree of freedom, is actually, we say, eaten by the fact that the photon inside the material becomes massive. And that's what we call the plasma. Okay, so the Goldstone boson disappears to give mass to the photon inside the material. That is what we call the plasma. And this is really what makes possible the Meissner effect. So you see, Anderson had things pretty well understood, and says here, these two types of bosons, I mean the one that comes from the U1 symmetry and the one that should be there, the zero mass Goldstone boson, seem capable of canceling each other out and leaving finite mass bosons only. So this was observed in 1962. And so that's why there is no Goldstone boson here, because we have the plasma here when we break the symmetry in BCS superconductors. Of course, then Higgs wrote in his own paper, the purpose of the present note is to report that the spin 1 quanta of some of the gauge fields acquire mass, okay? And this phenomenon is just the relativistic analog of the plasmon phenomenon to which Anderson drew attention. So Anderson was really the first one that was able to see clear this connection between gauge theories and spontaneous symmetry breaking. So the Higgs mechanism and the Higgs boson. So as I hope I convinced you, the Higgs mechanism implies that there is a fundamental scalar field with self-interactions, which can cause spontaneous symmetry breaking in the vacuum, respecting all the choreography of the gauge symmetries. And the important thing is that can give masses to the gauge bosons. So that's what we need to have the weak interactions. We know that the weak interactions are short range, and therefore the carriers of the weak interactions, the W and the Z boson, need to have mass. And in fact, I was lucky to be here in Stockholm in 2013 at the Nobel Prize ceremony, and Mr. Higgs was telling me and my good friend and colleague, CERN Director General Fabiola Gianotti, he said, my first paper, I'm sorry, you cannot see it here. Okay, let's move it. My first paper was rejected because it was not relevant for real physics. Okay, so now Mr. Higgs said in the second version of the paper, I actually explained that the way one can prove the existence of this visible energy field is by looking for a physical particle that is the Higgs boson. And so this is what happens, correct? They are in SU2 cross U1 is broken to U1 electromagnetic. And so we have originally 4 degrees of freedom. 3 of them here are Goldstone bosons that are eaten to give value to the W and the Z boson. And then 1 Higgs physical field is left in the spectrum. Okay, so this is the system. So with that was possible to really give birth through the Higgs with the Higgs mechanism in mind to the standard model of particle physics by Weinberg and Salam. So we have, as I told you, the SU2 cross U1 non-abelian gauge theory that we had originally in the standard model. This is spontaneously broken. These are 4 generators here. 3 of them are the ones that are broken, and 1 is left unbroken and is U1 electromagnetic. So there is basically the photon left without mass, and the W and the Z bosons with mass. And this is what I wrote here, 3 of the 4 Higgs components. This is a 4 Higgs components because it's a complex doublet, are eaten to give mass to the W plus, W minus, and the Z, leaving 1 neutral Higgs boson and the well-known massless photon in particle physics. Of course, there is another piece of this standard model, and is that there is a new type of interaction that is called Yukawa interaction that makes the Higgs talk to all the matter fields, to all the fermions, and when this Higgs is also turned on or acquires vacuum expectation value, it gives mass to all the fermions in the standard model. And the heavier the particle is, the stronger it talks to or it interacts with the Higgs boson. So, okay, so what happens is that, as I told you, Mr. Higgs says, go and look for the Higgs boson. And my friend Fabiola and his colleagues actually indeed went to look for the Higgs boson, and they discovered the Higgs boson. So it was half a century after the Higgs idea that it came the discovery. So it was exactly July 4th, 2012. And as you see, was a big splash everywhere, and certainly brought tears to Mr. Higgs' eyes. So what it took to make this such a discovery, remember this was a new type of particle, so it's a spin zero scalar particle, and was a new type of interaction, that is this Yukawa interaction that was not seen before, a new type of force. So what it took really was to build the most complex, most expensive, and machine ever built by humankind. And this is the Large Hadron Collider that is here in this picture. And so this is a proton-proton collision, a proton accelerator, 17-mile ring, 300 feet below ground. And it is spanning in the Swiss-French border at CERN. And clearly, you know that your experiment is really big when it's quite big compared to an international airport. To look at what happens there, we have big cameras. The biggest one that discovered the Higgs are the CMS detector and the Atlas detector. At CUNY, actually, there is a group in Atlas. So this is the Atlas detector. It's the biggest, the largest detector in the world. And here you have a person as comparison. And so with this detector that is kind of made of multiple layers, we can really go and look at how the Higgs is made, and we can see it. So obviously, building the Large Hadron Collider was essential, but in reality, what made the discovery of the Higgs boson possible was something else, besides having the biggest machine in the world, and it was the effect of virtual particles. So all the fundamental particles of nature that we know can behave as virtual particles as a result of the Heisenberg uncertainty principle. And what this means is that there, for a very short period of time, it is possible to have a large uncertainty in the energy so that virtual particles can flicker in and out of existence in a very small time. And this is what happens actually. And so this is for me, and I think for most of us, a mind-blowing feature of the quantum world, but it's crucial in most of the experiments that we do to really be able to have the measurements that we are able to do. So these amazing virtual particles are the reason that we can produce the Higgs boson. In reality, these are two protons that are made of a lot of quarks and these wiggles that are gluons. So what we do when we collide the protons, of course, what we collide really are the fundamental particles inside the proton. And you would think that what you collide, that you would produce the Higgs by collision of the heaviest particles possible. But in reality, no, because what we do here is that the gluons, the best and most effective way of producing the Higgs is by colliding two of the gluons inside of the proton, as you see here, okay? And the gluons do not talk directly to the Higgs because they are massless. So what happens is that the gluons collide in this quantum vacuum and create these virtual tops, these virtual particles, okay? And the virtual tops are the most massive particles and talk a lot to the Higgs in this interaction here because it's proportional to the top mass. And so they create the Higgs. The Higgs then actually lives for 10 to the minus 24 seconds, or about 100 yoctoseconds, and then decays into lighter particles. And these lighter particles could be a pair of photons that also are created because of the existence of the virtual top quark particles in a loop like here, but where you have the Higgs, the top quark, and then they decay to, instead of the gluons here, they decay into 2 photons. Or for example, the Higgs can convert into 2 of the Z boson particles that are also virtual, and these Z boson particles decay into electrons and muons. And we are very lucky. What I try to show you here is as a function of the Higgs mass that we have measured to be 125 GeV, because there are many, many channels. So this is the Higgs going to photons, the Higgs going to BB bar, to Ws, to gluons. So we are in a region that is very lucky, because there are a lot of relevant channels, so that we can really study the Higgs and understand if the Higgs, or the particle we think is the Higgs, is really behaving as it is predicted in the standard model of particle physics. So without the virtual particles, the Higgs discovery would have not been possible. And before moving on to the next topic, let me just say that, so here's 2 examples of the actual first events of the Higgs discovery. A Higgs going to 2 photons. This is inside the CMS detector, and we see the 2 photons coming out of the debris, making the Higgs in the proton-proton collision. And here is in the Atlas detector, there's a Higgs going to 2 Z bosons and then decaying into a pair of muons, the blue tracks, and a pair of electrons, the green tracks, inside the Atlas detector. So now, so this was done in 2012, and the LHC is going to be running in phases until 2038. And why we are doing that is because of all the things I was telling you here, that the Higgs is actually, so that the Higgs is going into all these particles. We really want to study how the Higgs transform into all these particles. And this is what we are going to do in the LHC. So is what we call precision measurements. It's really, for example, only 2 years ago, it was proven that the Higgs actually talks to the top quark and to the bottom quark. It took, almost 8 years to understand that. So from one side, we are going to, measure the properties, the behavior of the Higgs, the best we can with very high precision. This is the precision of which we measure the coupling of the Higgs to photons, like, less than 2% is the projection for 2038, and so on and so forth. And on the other hand, of course, we want to make new discoveries. We want to use the Higgs as a tool for understanding the existence of other particles. In particular, castings of the Higgs that I will show in a moment. They're super interesting, for example, for the matter-antimatter asymmetry of the universe. Or maybe looking at the Higgs talking to new forces, or talking to the dark matter that we don't know what it is made of. And I remind you that we will have in this time scale 30 times more data at the slightly higher energies of the order of 14 TeV at the center of mass energy. Okay, so we got the Higgs boson. We are very happy because was billions of dollars invested in the Higgs to discover, in the LHC to discover the Higgs. And we are going to use it as a tool to discover. So now what is next? The next challenge I want to talk to you about is dark matter. Okay, so dark matter, we know that dark matter exists because galactic and cosmological observations show that there is much more matter in the universe than what we see. And the strong evidence of this dark matter, and the first evidence for this dark matter, came through interactions with visible matter in galaxies as our own Milky Way. And in fact, it was in the 1970s that Vera Rubin and her colleagues started to measure how fast stars are moving in galaxies like our Milky Way. This is not the Milky Way, but like our Milky Way, as they orbit around the center, the visible center of the galaxy. Our sun is in this, if it were this the Milky Way, the sun would be around here, correct? And so you see that she found that this is what she observed, okay? And this would be the prediction of the velocity of the distant stars from the center of the galaxy if we will consider just a standard Newtonian gravity. It has to go like this, correct? Instead, she measured basically that even the most distant stars here are moving with about as fast as the stars that are close to our sun, again, here. And this obviously contradicts the standard Newtonian gravity and implies that something else something invisible is holding these stars together, that they are moving at these high velocities. Of course, things have developed, and nowadays we have many other sources of evidence for the existence of dark matter coming from different observations. And one example that I'm sure you're aware of is gravitational lensing. So as Einstein told us long ago, space-time is distorted by the gravitational effect of matter, and that makes the light of distant objects to have curved paths as they reach us, okay? And the effect of this gravitational lensing is to distort images the way we see it here in the telescopes when we look at them. So today we have relevant computer simulations and that can transform these distorted images of galaxies into where the matter should be. And this mass distribution of cluster galaxies that comes from these gravitational lenses, for example, in this picture, so a galaxy is like one of these spikes. So we see a lot of spikes, point-like spikes here, but there is also a distribution here, like a mountain of where matter is, and this is actually where dark matter is situated. Of course, this is another interesting thing of dark matter, basically almost at today's time, I would say, that is galaxy cluster collisions. And here we see the bullet cluster that was discovered in 2004. And so two galaxies collide, the X-rays, the hot gas is left behind, and what is the dark matter that we see through gravitational lenses goes through because it's collisionless. And so this analysis tells us a bit how dark matter behaves. For example, how much self-interactive dark matter could be there, or how are the properties of the dark matter. Finally, there is also, of course, evidence for dark matter that comes from larger redshifts or earlier times, let's say. And that's, as you know, is the CMB, the cosmic microwave background spectrum. This was emitted 380,000 years after the Big Bang, when the temperatures were of the order of 0.3 electron volt. And the atoms first became stable at that time, so the photons start free streaming. And so what we measure here, these colors of variation in temperature, what you measure really is the variation in temperatures by measuring the photon density at fixed frequencies, and we can know if this there was an overdense and or underdense. Underdense means colder, overdense means hotter population of photons with respect to what we expect to the background temperature of 2.7 Kelvin. And so you see, because the photons were in equilibrium, in the temperature of the photons were in equilibrium with the temperature of the hot gas, we can learn a lot about, from the CMB power spectrum, we can get information about these peaks here that tells us the ratios of these peaks, and analysis of this behavior tells us, for example, what is the curvature of the universe, tells us a bit, the ratio of these tells us a bit about how much baryonic dark matter is. And the third peak is the ratio of matter, mainly dark matter to photons. So this is the first measurement that we have of direct evidence of dark matter at recombination era. The other thing that we see here is the matter power spectrum. And what we see there, so the matter power spectrum describes the density contrast of the universe as a function of a scale. So it's the Fourier transform of the matter correlation function. And we see that this starts, if you see, at redshifts of order 30 and goes down up to today almost. So z equals 0. And so what we start when basically the first small structures start to evolve when the universe was like less than 1% of its current age. And the interesting thing is that if we do these simulations with lambda CDM, so if we do simulations, we observe, for example, these are these dots here, these red dots here, are actually observations from the Sloan Digital Scale Survey, and instead the black curve that is there is actually the Lambda CDM model. And we see that if we put 85 of dark matter, so pressureless matter, and 15 of conventional baryonic matter in this simulation, we really very well describe what is going on in these powers, in this matter power spectrum. Instead, other options like no dark matter, the dash, or other like, the form gravitational behavior will actually give us spectrums that are matter power spectrums that are very far away from what we observe. So I hope I convince you that there is dark matter. Now the question is, what do we know about dark matter? And the answer, unfortunately, and you know that from the beginning, is very little. Because all what I show you is that dark matter couples gravitationally to us. So the only real information I gave you is that through gravitational interactions. Of course, I also show you that this is the most abundant form of matter. So 85% of matter is in dark matter. And we do know that it's something different. It is not baryonic. It doesn't behave like the usual baryons that we know. But we don't know what it is. It could be new particles. It could be some compact objects. It could be very light particles that behave much more like a wave-like disturbance. And so this makes very challenging to search for dark matter. Okay. The other important thing is that we are thinking, dark matter could be a combination of many things, and could be a part of a much larger invisible sector, or dark sector, as we want to call it, with new dark forces that we have not discovered yet. Okay. So the point is, there are some things we know. We know, that the mass can be anything between something like 10 to the minus 22 electron volts, and this is because we need to have a de Broglie wavelength that is sufficiently small so that you can form dwarf galaxies with dark matter, and it can be sufficiently heavy, and as heavy as we have proven that that we have not seen, for example, heavy compact objects. So this is a very broad range, and so it's very hard to find dark matter and to search in all these areas to understand what is dark matter made of. However, there is one interesting point that has been explored a lot, and is that folding in assumptions of how the evolution of dark matter occurred, the dark matter density in the early universe, can tell us a little bit more about the energy scales. And this is what I try to show you here. So this is the whole region of dark matter. But if we think that dark matter at some point went into a freeze out, and we were left with the dark matter density that we see today, in most cases, if we assume something about this early universe cosmology, and we assume that the dark matter was in thermal equilibrium, basically at the moment of the freeze out, then this narrows quite a bit the region of masses that we can think of. And this I'm sure you have heard of. So if we look now to what is thermal dark matter, for the past 2 or 3 decades, we were thinking on this corner here that we can have weak standard model charges that can be a part of an extended standard model sector. And we call it that weakly interacted massive particles, or WIMPs. Okay, so the WIMPs are actually a bit of a miracle, in the sense that if they are of the electroweak scale and with masses that are basically between about 2 GeV and 100 TeV, you can have thermal WIMPs. And we expect to have couplings that we could go and search for, either by producing dark matter at colliders, or by looking with very deep underground detectors that I will mention in a second. However, there is another region of thermal dark matter that is called altogether here the hidden sector, and this hidden sector has a lighter matter region, where the interesting thing is that if we are in this region, there should be some mediators that are a bit heavier but still light. And so the mediators could be new scalar particles, new dark photons, or other types, or neutrinos. And if that happens, then there is more to be searched for to explain this type of lighter matter. Or it could be heavy of the order of the WIMPs. But in any case, in this area here, the hidden sector and the WIMPs have signals or searching strategies that are very similar. In this lighter matter region, we are exploring a total new region for dark matter. Okay, and so there is a lot of work being done in different areas to try to pin down this lighter matter that is in the region between a KV and 1 GeV or so. Okay, so as I said, there are many possible dark matter particles. These appear in nature. And one of the examples I will give you is the one I added here that was not in that option, that is these light fermions that are pretty cute. And so there are many options. There could be weakly interacting type of particles, there can be neutrinos, there can be these very light bosons, there can be all types of modified gravity on some macroscopic behavior, or other type of light self-interacting particles. And so so we theorists have been thinking about all this, a bit driven by the fact that it has been very hard to measure, to know exactly what the dark matter could be. And also another issue that is important that I will mention briefly is that although lambda CDM predictions, so the cold dark matter predictions, have been able to explain very well all what we see at large scale structures, there are some tensions at the level of galactic observations at small scale structures. So, so let me just remind you very briefly that basically what we do is we can create dark matter in different, we can search for dark matter in some more standard ways. The standard ways are underground, so direct detection of dark matter. So the dark matter comes and hits basically a single nucleus in the detector underground and can be observed. We can look at dark matter like in this option where dark matter annihilates into dark matter and provides some standard model particles, and we do that in the space looking for extra signatures of gamma rays or neutrinos or positrons. This is the AMS detector that is actually in the space station. Or of course we can generate dark matter at colliders. We are very keen of doing that because in the collider we kind of know in which way we put the energy, and we can look what is the outcome of the energy we put, and in particular in the direction of a transfer energy. So perpendicular to the beam, we know we didn't put any energy. So if there is a imbalance in transfer energy, it could well be that there is dark matter that actually was produced and escaped our detectors. Of course, we will need to find dark matter in more than one way in order to be sure that we understand it. There are other ways that I will, for time, I will not go into, but let me just mention this cosmic prose. As I said, it's important to say that there are the dark matter, the dark energy plus cold dark matter paradigm is very good at explaining, as I said, predictions at large scale structure. But if you see at small scale structure, these M-body simulations can be very different if we put cold dark matter or if we put other type of effective theories of scale structure. And so the idea here is that we are trying to look at this small scale structure that needs to be much well understood, and we are in the process of doing that now, to explain, to understand what is the nature of dark matter. And I have to say I'm learning a lot about this because my son is doing his PhD thesis on this area. So, let me just show two examples of all what I told you. One example is this interesting light fermionic dark matter. And what this means is that there are possible new possibilities, really, of looking at dark matter with different velocities and different compositions. So this is the amount, the fraction of dark matter. This is if all the dark matter would be these light fermions, or if just only a fraction. And all these areas that are shaded are excluded, basically because in these areas, the main point to understand here is that because these are fermions, there is a fermionic degenerate pressure, which means that when we start, putting dark matter in different levels, we are necessarily going to have a high Fermi momentum because of the Pauli exclusion principle. And what this means is that there is a moment where dark matter, fermionic dark matter, although could be behaving as cold dark matter today, becomes non-relativistic at early times. And if it is becomes relativistic. So although it's cold dark matter today, it becomes relativistic at early times, and therefore pose a lot of constraints that come from contributing to the number of effective neutrinos that are relativistic, and that will change measurements in cosmic microwave background or Big Bang nucleosynthesis, or it can suppress the matter power spectrum by staying relativistic until too low redshifts. And this is a new results that we have just obtained in this paper with excellent postdocs and students, where we see that we open a region of parameter space that was not open before. We still say that in some regions of space, these small scale structure constraints are going to make it impossible for this dark matter to be there, because it will change, for example, the matter power spectrum or the delta effective in this area. But more interesting, we have found regions where it would be very interesting to think about new type of crystals that could be sensitive to dark matter velocities more than what we see in the Milky Way. And you can search for this new type of dark matter in new type of detectors, which also could imply some quantum sensors. Okay, so of course, I think I have to speed up a little bit here. There are also other possibilities of SUSY WIMPs, and I will come about that later. So let me just go into two small areas. So dark matter exists, and we are leaving no stone unturned until we know that what it is made of. So now let's try to see if we can say a few words about two big questions: how the matter-antimatter asymmetry came to be. And I think because of time, I will be small here, be brief here. So what I want to say here is that basically in the nascent universe had equal parts of matter and antimatter that should have instantly annihilate into one each other. And we are still here. And this is a nice discussion to watch, because here there are experts in the field, many, and they are discussing the many types of matter-antimatter. So if you would like to learn about it, I recommend it. But the basic is that matter and antimatter are governed by the same interactions. We know that the only antimatter that we see in the cosmos is what comes from secondary decays of the emission of antiprotons. And we have been able, by measuring the abundance of primordial elements in areas of the universe that we think has not been particularly affected after nucleosynthesis, we are able basically to pin down the ratio of baryon to photons, which is what is here. And this tells us that this is a very small amount of matter-antimatter asymmetry, or NB, that is left in the universe. And I will not go to the details, but let me just say that what we do not know, so at the beginning of the universe, matter and antimatter was equal, then they annihilated after the Big Bang. And so what generated this imbalance between matter and antimatter? Sakharov told us that there are the three principles that need to generate matter to generate a matter-antimatter asymmetry. One is that either baryon or lepton number should be violated at some point, because if the universe is not symmetric and nothing is violated, you cannot generate anything. Charge and charge parity should be violated because those are the symmetries that basically treat different baryons and antibaryons, so that we can make a difference between matter and antimatter. And also there should be some out of equilibrium process, because if the one process going to one side and process in the inverse side are equal, then of course at the end you will wash out whatever you put. And there are different possibilities that, because of time, unfortunately I won't say anything, but I would like to say a few words about what we call generating the matter-antimatter asymmetry at the moment where the Higgs turn on. So we are putting together these now with the Higgs, and probably I will again be succinct here, but the idea is that we start at the moment. So this is our Higgs is turning on at the moment of the electron-weak phase transition, so instance after the Big Bang. And so we have these bubbles of broken symmetry in the symmetric soup of Higgs off and Higgs on. And so the idea is that we are trying to generate the matter-antimatter asymmetry as the universe is, as these Higgs on bubbles are expanding until they basically take over through the whole space. So the bubbles expand and near the speed of light, and then they create these non-equilibrium processes. And so we have looked at many details, and I unfortunately will jump over them, but the idea is that we have to have a first order phase transition, which means that from the electroweak symmetric case to the electroweak broken case, so from here to here, we have to do it in the discontinuous way instead of in a continuous way. And if we do that, we can be sure that with CP violation, there is the possibility of creating some asymmetry between left-handed and right-handed particles, and then some configurations that are called sphalerons, and are basically some configurations connected to the Higgs and gauge fields, are able to only see left-handed particles, and they tend to erase any difference between baryons and leptons. They try to change baryons to leptons, and these sphalerons are the ones responsible to generating the baryon asymmetry at the electroweak phase transition. But as I said, the important thing is that the sphalerons are very active in this area where the Higgs is off, but once the Higgs is on, we need the sphalerons to turn off, because otherwise they will wash out all what we have done. And I would be glad to tell you more about it, but if you want to ask. The thing I want to say is that we have looked at this idea that the sphalerons are responsible for making the baryon-antibaryon symmetry of the universe in the standard model. All the ingredients that we need from Sakharov are present in the standard model, and I list them here. However, after we found the Higgs to be 125 GeV, we realized that this is not possible, because the Higgs basically is too heavy in order to have this continuous transition at the moment that the Higgs turns on. So if we want to still explain the matter-antimatter asymmetry at the electroweak scale, we certainly need to have new physics. And this is one of the main reasons there is plenty of work in the field thinking about how cousins of the Higgs field are responsible of triggering the matter-antimatter asymmetry at the moment that the Higgs turn on, at the moment of the electroweak phase transition. And I have worked on that a big part of my life, so it's very exciting. Of course, the other ingredient is CP violation, and I did not go into very much detail, but this is an area that is fascinating, because there are experiments like electric dipole moments that put a strong bounce on CP violation. And on the other hand, you need to have enough CP violation to actually generate the 610 to the minus 10 ratio of baryons to photons density. So the other thing that again is excellent here is that we just have heard that was the discovery of gravitational waves not so long ago. Well, a first order phase transition naturally trigger gravitational waves that are associated to the sound wave when the transition occurs. So let me see, just in 2 words, that this type of analysis has a lot of results for phenomenology. Both are I won't explain this, but we can look at double Higgs production at LHC and future colliders, and see if this there is an enhancement of this di-Higgs production of 30% or so. That could be a signature of this electron barogenesis. We can also look for gravitational wave signals. These are, for example, reach of LISA and BBO, and these lines here are models of this singlet extension of the standard model, where this will be the signatures of gravitational waves that are going together with phase transitions that would actually explain the matter-antimatter asymmetry. So maybe the last few minutes, Michael, tell me if it's too late. What I want to show is, okay, electron barogenesis is an interesting playground. They require the existence of more Higgses beyond the Higgs we have discovered, and it could be connected to the invisible dark sector and dark forces. And so the most interesting thing is that if there are these new particles, as I told you before, these new particles, all particles that we know of, can go into this virtual particle state for an instant of a second, thanks to Heisenberg uncertainty principle. So if there are new particles, it will be new neutral particles, okay? So the idea is, can we take finally a closer look at where we can look for the existence of new virtual particles? And of course, I'm guessing you, well, this is maybe a bit too much, but this is just looking at the April 7, 2021. I was watching the Fermilab presentation of the muon G-2 experiment. And because it's late, I will go on. So this is the experiment. Please take good care of this beautiful blue magnet here. So as you know, muons are copious in cosmic rays, but here at the Fermilab experiment, we produce muons in very controlled conditions by a particle accelerator that creates the muons that enter here and go around this ring in a vacuum with a magnetized loop at almost the speed of light, and we look at what these muons do until they decay. So the goal of this experiment is to measure something that we call the G factor, and the G factor has to do with the way, the strength with which the spin of the muon precesses in the presence of a uniform magnetic field. And when that, in reality, what this experiment does, it looks at the difference between the precession frequency of the muon spin and the cyclotron frequency of the muon when it goes around the ring, both in the presence of a uniform magnetic field. This is another whole story, which is great, but this 50-foot long ring of magnets was first used at Brookhaven, and 20 years later, or 10 years later, came to Fermilab through oceans and the Mississippi and highways, and arrived to Fermilab on this stormy day. So we are using the same 50-ton ring that was used for a similar experiment at Brookhaven. So what do we do here? As I said, we measure the precession frequency of the muon here, like a gyroscope, correct, in the presence of the magnetic field, and is proportional to this G factor. And then, of course, when the muon in the presence of the magnetic field, the muon that is a charged particle also goes around the ring almost at the speed of light. And this is what we see here. So we measure the difference of these two, correct? And as you see, if you do your calculation here, the difference of these two frequencies is proportional to this factor G-2. So what we see here is we create the muons smashing protons to the target, then the pions decays into muons and neutrinos, and the muons are injected here. The red lines are the direction of the muons that, as you see, go around the ring because of the magnetic field. And then there is this yellow, this is the spin. So it starts the spin and in the case of muons, negative muons, the spin and the direction of the muon are aligned. But because of, as I will show, because of virtual particles, there is this wobbling of the yellow versus the pink arrow, is this wobbling of the muon. And what we measure in this experiment is this wobbling of the muon, how much the muon wobbles, because this tells us with which virtual particles the muon is interacting. Okay, so this is what it is. So if the muon would be in the vacuum on its own, without any virtual particles, then this is what will happen. No? The spin and the muons will go around always aligned. But because the muon talks to virtual particles, then there is this wobbling, correct? And in other words, of course, we can compute as theorists all the effects of the muon talking to many particles. So these are photons and electroweak particles and all the hadronic QCD contributions. So everything needs to be taken care. And it's a very strong tour de force. So basically the muons, for an instant of a second, talk to a virtual photon and a virtual muon, and then become again the usual muon. So we can do this computation very carefully, and we are going also to measure this at the experiment. We measure this at the experiment, and we can see if what we measure, we can compare the wobbling of the muon that we measure with the wobbling of the muon that we predict. Okay. Of course, what we are computing is the muon talking only to standard model particles. And maybe it's just a comment that in reality, we cannot really look at the spin of the muon, but we have a sophisticated way to look at the decay of the muon into electrons or positrons and neutrinos or antineutrinos, depending if it is a positive charge muon or a negative charge muon. And depending on that, we can look at the energy and the arrival time of these electrons, which is related to its momentum, which is related to the spin of the muon in the muon rest frame. And in that way, we can measure the wobbling of the muon. So it's impressive. When I was looking at my colleagues talking about this, I was like, wow, it's impressive they can measure this with such a precision. Okay, so by doing that, we are able to measure the G-2. And voila, the Fermilab experiment measures significant more wobbling than was predicted by the standard model. Okay, and in reality, as you see here, it makes the New York Times, the particles tiny wobble could upbend the known laws of physics. Okay, this was done, as I said, the presentation of the final results. Even Michael Bloomberg said the most extraordinary event of the year. So we really reach out, and even more, Luke Skywalker said that the force must be with us. So it was really impressive, and the results are these, correct? So the results is, this is the experimental result from Brookhaven. In some, basically, we take away the standard model, so we measure the delta in mu, the difference between the experimental value and the standard model calculation. And so we see here in an upshot, this is the Brookhaven result, this is the Fermilab result. I mean, I want to tell you, this is a 20-year apart experiment, totally independent. This result could have been here, correct? Could have been anywhere. So it's amazing of the precision. So this is the average, and this is the standard model prediction. So they are basically, they are 4 and 4.2 sigma standard deviations away. And there are some subtleties. There is more data coming, 10 times more data will be analyzed by the muon G-2 collaboration next summer. I do not really think that the result, the experimental result, will change. A caveat is the theory result, because as I told you, these type of calculations here, these QCD calculations here, you can have anything you want of hadrons. These calculations are done at very high order of precision with very sophisticated non-perturbative methods, lattice calculation methods, and they are very hard. And so there is a small, this is the many groups working together for a long time. This is one group who claims something different. And so there is a lot to be, there is a lot to be said in the next year or two. But I would say, I don't expect this to change. And it's unlikely, I think, that this will change, because if it will change, there will be tension with other experiments that have been done for over 20 years. So a message from the void means, are the muons talking to virtual particles we have never seen before? You know, that would be amazing, correct? So theories are proposing many scenarios with new particles and new forces. And here you see some of the physicists who have been working very hard on trying to challenge our understanding of modern physics. There are many possibilities. I will mention a couple now in the next to last slide. So there are new forces that are these leptophilic gauge bosons or Z primes. These are interesting particles that could connect with our matter, that could explain the small tension in the Hubble constant between recent and earlier measurements, as we see. There are new scalars that could play interesting roles in baryogenesis, or can play interesting roles in collider physics, that are light scalars that could also explain the G-2, as you see in this area, or here you see in this area. And here is an example that is dear to my heart, that is supersymmetry. So in the good old supersymmetry, you can explain the G-2, you can explain dark matter, and you can have searches that you will probe at the high luminosity LHC. So if the answer is supersymmetry, through basically, the interesting thing in supersymmetry is that the actual contributions to the G-2 are actually coming together with the same particles that will give you a dark matter explanation in supersymmetry. Okay, so that's interesting. So I think finalizing, I would like to say that we are trying to decipher one puzzle piece at a time. We are searching for many new ingredients of nature at experiments, and we don't know where nature can show us new signatures, but virtual particles is obviously an interesting point. And this is, I want to finish that. So first of all, I would say, if you like to read more about this G-2 and the unseen universe, this is a cover article about the G-2 in Scientific American of October. And then you see the same ring that I showed you before, correct? The G-2 ring, magnetized ring. And this is me, of course, in a visit a few weeks ago. But you see that there has a different color. And I was there with one of my colleagues and said, what happened? What's going on here? And he said to me, well, you know, Marcela, you know that in G-2 we are really, you know, the precision and the level of accuracy and the high level of technology that we are using is really unprecedented, and that's true. And so he said, so we were trying to do and use the best technology, the most advanced technology, and we discovered that we have a problem with regulating the temperature of the experiment. So we decided to use the absolutely most ancient technology ever, and I hope you guess it, that is a blanket. So they put a blanket over the experiment. So still too much to discover. Please stay tuned, and I am open for questions. Thank you.
Well, let's open it up for questions. Any?
So I don't know if you want me to, yeah, either stop sharing or.
Yeah, I'll stop it for you.
Okay, so that we can have more of a
Okay, there, you know, I guess somebody else did that.
Okay.
So that was quite a tour de force. It was a tour to a lot of really deep ideas. And so let's open it up if anybody has any questions. Tony?
You are muted.
You have to unmute yourself, Tony.
Okay, all you missed was thanks, Mike. Hi, Marcela.
Okay.
So it occurred to me it occurs to me regularly that what we usually do is theorists produce models and experimentalists go and look for them and don't find them. And so I just wanted to get your reaction to the other way of doing things for experimentalists, at least, which is just to go out and measure every single thing we can and compare it to the standard model prediction. And I know it's not that appealing for a theorist because you're building models and you can't really do very much with those kind of results, but just in terms of a way of looking for new physics without being bound by models, which, with all due respect, are often kind of arbitrary.
Yeah, so there are many efforts, as of course you know, and especially thinking about machine learning and other approaches or effective field theories, correct? Where you're trying to do the most model independent explanation or search that you can. So I see these two ways. In my first answer to you would be, maybe when I was younger, I would say I used to build my little model, which I like, and then we'll go to you and said, could you please go and look at it at the collider, correct? But now I think we have taken, maybe because we are desperate for signatures and guidance, we have taken the opposite approach. So when we said, supersymmetry is there, go and look for it, it was more on a theoretical push basis. Now we have the G mu minus 2, and there's something that, the standard model gives a result, the experiment gives a different result. Or for example, in LHC and LHCb, you have their case, correct? B going to K mu minus goes 85%, and B going to K E plus E minus goes of order 1. And so there's a difference between electrons and muons that, again, is not in the standard model. So all what we have is a standard model. So I think we have one part of maybe your answer is we have now taken the approach that we try to see where are things that we don't understand with our standard model theory, and then try as theories, try to see how to put the pieces together, correct? And so, for example, one thing I didn't talk about, but G mu minus 2 is about muons, and RK is about muons being different from electrons, correct? So maybe the muons are telling us something, and so we are trying to put together, for example, the two anomalies. One is 4.2 sigma, the other one is 3.1 sigma or so. Maybe, you will not be excited about the 3.1 sigma, but it's persisting, correct? And so it is very challenging from my point of view to try to find a model that could do good things and explain the two anomalies. And of course, if I can also explain dark matter or the matter-antimatter asymmetry, would be even happier. The other thing that probably you are asking for is just being more agnostic and saying, let's try to devise searches that are totally model independent. And we can do that. We are doing that to a certain extent, but maybe not as much as you would like. But from my perspective, I like to take the first approach, right? Where I try to see where the experiments are telling me that something is not matching to what we expect from the standard model, and try to see how I can explain it. So I'm looking at the experiments much more than I ever looked before, I guess. Is that a good answer, Tony?
Yes, it is. Thank you. It still seems like the phase space of possible things that explain G minus 2 is near infinite.
Indeed. I mean, you can explain G minus 2 with whatever you want. The point is if you can use it to get guidance for something else.
Right.
Okay. So if you put G minus 2 and RK, you are in deep trouble. It's very hard to fit things together. It's almost impossible. You have to make complicated models. So it's not very nice from the theory point of view. If you say, I would like G minus 2 in the supersymmetry, and I also get by free dark matter, instead of having to put, this part of my theory explains G minus 2, and by the way, I need dark matter. So let's put something else totally disconnected that explains dark matter, correct? So that would not be my preferred approach.
Yeah.
So, but you're right. G mu minus 2 can be explained with a lot of things. Anything that talks a little bit to the muon can do the job. Well, not everything, but
yeah,
a large variety.
Okay, thanks.
Anybody else? Yeah, I have first a comment and then a question.
Okay.
I go way back with G minus 2. I worked on it for about half a dozen years.
Mm-hmm.
And I really want to give credit to the person who came up with the idea for it, and that was Francis Farley. And that goes back, I think, to he was at CERN.
Yeah.
And he was the one who conceived of this, and he did the first measurements. Having been involved with the experiment in the early stages, and in fact, one of the things that I was working on was the development of the magnet, I am very confident in the results. I know a lot of the people who worked on it. And so from my point of view, the experimental results are really probably rock solid.
I agree. I agree with you.
Which then leads me to my question. In actually doing the calculation, you have a lot of hadronic terms that you had to that have to be considered. Is there any room for wiggle in that? That's kind of what I'm basically saying is don't worry about beyond the standard model, but just in general, in terms of the calculation, how would you assess that? Yeah,
clearly, the first thing we need to understand, and I didn't have enough maybe time to look at it, is that the standard model calculations, forget about new physics, correct? The standard model calculations at the moment, the lattice standard model calculations of the hadronic vacuum polarization, rely quite a bit on experimental data of E plus and minus hadronic cross-section from like Babar and Clow and so on, okay? This is because we have not been yet powerful enough with our computers in lattice calculations to do it from first principles. This BMW, which is not the car, is Bielefeld something and Wuppertal. They claim they are doing it from first principle, and you can do it from first principle. The problem is that if you do it from first principle, your error is too big, and so it's not useful. The point is to do it from first principle lattice calculations without using the E plus E minus hadronic cross-section data and having errors that are commensurable to the things that you need. And that is what is trying to be there is a huge called the Theory Initiative that actually was started by Aida Al-Qadra at Fermilab, but it's a collaboration with Europe and the US and many other places, trying to put all the efforts to do this first principle calculations of the HBP without relying on any experimental measurements. Of course, if the results of BMW were correct, then the problem is that would point to a tension on this E plus E minus hadronic cross-section. So you will go from having a problem in G minus 2 to having a problem on these E plus E minus hadronic cross-sections that have been measured by many groups for decades. And so it's a bit it's a bit complicated because it's not easy to, many people more expert than me have been looking at this, and it's not easy to put the pieces of the puzzle that you say, okay, I understand that this is my real calculation, it's very much okay with G mu minus 2, as this BMW will say, and then how do I explain the results of hadronic plus and minus cross sections, which basically would give variations in the phi structure constant that would affect measurements of MC. So, people have been experts like Sirling, for example, and other people have been looking at this and trying to put the pieces of the puzzle, and it's not obvious. So there is always some tension. Of course, there could be, some under-evaluated systematic error that is it's for the experts to say, Michael. I can't say, but it could be correct that someone really screw up badly with the systematic errors. But in that case, that's why there are many groups trying to do it again before jumping up and down, correct, on this result. But as I said, it's not easy. It's not easy to say, my calculation was wrong, I changed it, and then at some other place, the tension goes somewhere else. Experiment with experiment.
All right.
So that's,
So anybody else want to comment on this or question? I'll make one further recommendation. If you haven't read the Scientific American article, read it. That's a beautiful piece of work for the non-specialist.
Yeah.
I think you did a remarkable job with it. I mean, this is really tough stuff to understand, and you made it comprehensible, I think, for a lot of people who might have read that. So thank you very much for that effort. And thank you very much for your talk. And I hope that your trip to Argentina does come off and you stay safe.
Yeah.
And we very much appreciate the time you took. I know you've been under a lot of pressure. Really appreciate the time you took to do this. Thank you once again.
Yeah, thank you. It was my pleasure too. So thank you for the comments on the article. I really enjoyed a lot writing it. It was a lot of work. So my very first experience, but I think it's nice to, you maybe have more experience, Michael, in connecting to the general public. I'm doing this now, and it's a lot of, it's very difficult, but it's a lot of it's a lot of fun. So thank you for the opportunity to give this presentation.
Thank you once again.
Okay. Bye-bye.